index key value K1, and we can have the pointer. What is it for? What's this pointer? This one? This is a pointer for data file. Okay? Actually, block. It's a data pointer. Using this pointer, you can access it, finally access the data. How many of them? In this case, key minus 1, we have 2 index key value and 2 pointer. First thing you need to define. When you design, when you model, when you solve the problem of the B or B plus 3, you need to determine the node data structure. Okay? In case P is equal to 4, you can have one more. Like the K equal to 3 and data pointer. We may have each node structure as 3 or 4. The children pointer. 4 children. Maximum. This is a node structure. So then there are 2 the operation when you build the B3 index. One is when you insert the data in case of full. There's no full means you fill up this one, this one, this one, then there's no more space. Then how can you address that problem? You can split it into 2, half and half. The middle value goes up, that is promotion. So there are 2 operations. One is split, another one is promotion. If you can understand this one, that's it. Okay? So I figured out how to erase. Much better. Right? Erase all of that. So then why don't we use this one again? Okay, so first the 8, 5 is inserted, then I'm going to simplify the node structure, but you need to, oops, I need more practice. Where is it? Okay, so I'm going to use the simplified one, but first you need to determine the node structure. So 8, when 8, 5 is inserted, it will be 5 and 8. Okay? Then next thing is the 7. 1. 1 is inserted, there's no more place to insert. Okay? Then it's a full. In case of full, you can split into 2. So how many data you have? 1, 8, 1, 5, 8. So which one is the middle value? 5. So 5 will be promoted. Then the left hand side goes to the left hand side. Right hand side goes to the right hand side. So it will be like the so 5, 1, 8, then promote 5. Then don't forget the children pointer. Complete the children pointer like this. Right? Then, in case the 7 is the next one inserted, the 7 is bigger than 5. So I can insert the index key value 7 to here. No, always you need to find the leaf node. That is the reason we try to keep the balance. Okay? So 7 is bigger than 5, goes to here, we have space. So it will be like the 7 and 8. In one node, it will be automatically the sorted. It's a little bit take a time, but we can almost ignore. Why? Because one block is the one IO, it will be loaded into the memory, then quickly processed. So we can ignore. Sort inside the block, same block. So the next value is 3. 3 is less than 5, goes to here, so 3 and 5. So this is a 3, this is a 5. It's not 5. It's supposed to be 1, right? This one is 1 and this one is a 3. Okay? Then the next one is a 12. When 12 is inserted, even though we have a space in parent node, we cannot use this one. Okay? Always need to find the leaf node, that is this one. What happened? It's a full. So we have the 7, 8, 12, this one is the middle value. So middle value will be promoted like this. And left hand side, the 7. And split into 2. So 12 goes to here, then 8 is promoted. Then don't forget the children pointer like this. Then 9 is bigger than 8, so goes to here, we have a space. So 9, 12. Then next one is 6. 6 is less than, bigger than 5, less than 8, and we have a space. So 6, 7. This is this one. Then we had one more practice last time. What if 0 is inserted? By the way, did I check the attendance last time? No. Did I collect? No? Okay. Did I say that I'm going to have the pop-up quiz this week?
No.
No. I cannot remember what the GA asked me. So I said in the classroom I'm going to have the pop-up quiz in the classroom. It depends on what you guys are doing, how much you guys show the performance. Okay, anyway, so after that, in case the 0 is inserted, one more thing. Some of the students are confused. What is the meaning of this sequence of number? This is the simplified index key value. Only the primary key 보이죠? Actually, when user insert the data, not only just the key value, also another data will be inserted, like the lead or address, depending on the data, the table format. However, to simplify the problem, so we are using only the indexed key value. Okay, don't confuse. Many of the students are confused. What is the number of? It's an indexed key. It doesn't have to be the primary key always. It can be secondary key, it can be the cluster key, so it doesn't matter. But it's an indexed key value. But if the 0 is inserted, the same procedure. So we can find why don't we use this one? So 0 is less than 5, goes to here, so no space. So always split into 2. And we have the 0, 1, 3. So 1 is the middle value, so 0 go to here, 3, and the 1 will be inserted. Unfortunately, parents know it's a 4. It's the same procedure. Then the split into 2, we can have the 2 pattern, and the 1, 5, 8. So 5 is the middle value. Middle value will be promoted, and 1, 8. So we can make this like this one. That's what we did before. What about remove the data? When we delete the data, what happens? This is when you insert the data, how we can manage the indexing structure. What about deleting?
You merge.
You need to merge. When? Less than a half. In case you have the data less than a half, you can merge. It's a little bit more complicated than the inserting the data. But idea is the same. In case less than half of the capacity, we can merge with the sibling. Okay? But I'm not going to explain about the removing the data. Okay? But idea is you can merge in case of less than half of the capacity. Any question regarding to the B3? Really? So I expect all of students can answer the B3 or B3 index?
Yes,
In
we
case-
have one question.
Yes. That doesn't mean I can excuse.
No question.
No question. So this is an index. Then I probably ask a question. Is there any issues when we are using the B3 index in terms of the query optimizer?
Yes.
Yes. Yes.
The same problem, like we cannot, if you want to find 50, then we can just start with
So for example, in the
That's 5.
Yeah, it's 5. If you want to find 5, then we can just find at the first node. So we cannot determine how much depth we should go.
so in other words, so what about the 5? When query optimizer access the data using this index that is indexed by 5, how many IO? 1, and using this one, 2. So 2 IO. What about this one? 3, 1, 2, 3. So what if when we have the level 10, sometimes 2, sometimes worst case 11. Usually the level of index is growing very quickly. Sometimes depth is 100, which means to access the index data, it needs 100 IO. Sometimes 2, sometimes 100 IO. So for the query optimizer, it's better than the search tree, but it's still not consistent. Okay, we cannot guarantee. There is an upper bound, but still, sometimes if you are lucky, you can access the data using 2 IOs, but sometimes more than that. So it's not completely fully balanced. So we need to address that problem. How can we address that such a problem? Any idea?
All the
Binary tree? We do not have a binary tree.
Balance.
Balance is a balanced, but not fully balanced. Why don't we make a fully balanced tree? Which means?
all nodes on the lowest level.
Yes. So this one has the data pointer. Why don't we put down all the index key value to the bottom leaf node? Right? So 5 goes to somewhere here, 8 goes to somewhere here. Then for the node, non-leaf node has only classify the data. Okay, branch the split the data. Okay, that's the idea. To make them, we need to have the little bit slightly change it, revise the indexing structure, B3 indexing structure, which is called B plus, so kind of enhance the B3 structure. So that is the B plus 3 structure. Before that, so this is the algorithm to be the B3 structure. When you see this one, this means to decide the middle value. So in our case, so for example, when we have the 3 different values, the middle value is this one, obviously. So no problem. But if we have the odd number, which one is the middle value? It's not like the average, okay? We are not going to average it. Unlike the median value, when you select, instead, cut in half, then either this one or this one. But in our class, okay, we will use the cut in half and left-hand side. That will be selected as the middle value. Is there any reason? No. Sometimes some of the DBMS use this one, some of the DBMS use this one. It doesn't matter. Okay, as long as you keep the consistency. But in our class, only for my convenience, when I grade you, exam answer, so we will use this one. Also this text will use the left-hand side the value in case of an odd number. That is discussed in the algorithm, very complicated. So many of the students got confused why it's just sometimes +1, whatever. It's just nothing but to select the middle value. Okay? Then you can follow the step as mentioned here. Also, we can evaluate just like what we have done in the single level index, multi-level index. So we can evaluate how much faster. For example, you need something the 23, the IOs to access the data using the B2 index, but I'm not going to explain details about it. But I hopefully, especially for the graduate student who are interested in such an indexing structure or the advanced data structure, I think they need to understand how we can evaluate. In this kind of evaluation, do we need any experiment? No, we don't need. Mathematics, simple math can prove the degree, how much we can improve the performance for when we are using the indexing structure. Okay, so this one shows the real example. In case of the 69% full node, as I explained, we are not going to use the entire 100% of the storage in the block, right? We set aside certain portion as a free space. Why? In case data is updated or changing, we need the additional space. Otherwise, it can be changed, it can be linked. Okay? So in this case, the 31% will be used for the free space. So each and most of the DBMS has the option how much you can set aside the free space. For example, Oracle database, you can change the value using PCT free, percentile of the free space in a block, something like that. So this slide shows that in case of the 69% the full, and in other words 31% of the free space, and then evaluate how many nodes we need to build the B3 index, B3 structure. Then B plus 3 is slightly different. Many of the students are confused the difference between the B3 and B plus 3. B3 and B plus 3, both of them are balanced tree, but the B plus 3 is a completely balanced tree. And also it has the leaf node. Only index key entry will be stored at the low level node. Okay, first level node. What leaf node? Sometimes we can use such a low level node. This one is called leaf node, or first level node, or low level node. So for example, when you are doing the project B, page 1, it mentioned the first level node. Okay? Sometimes there's no general notation. It depends on. In query optimizer usually mention the leaf node as the first level node. But in the data structure or algorithm, the subject, they mention the graph, consider this one as a graph, and this one is a leaf node. Okay, but no difference. So we put all the data structure. First, I'd like to show the difference first. So this is the final output of the B plus 3. Okay, using the same sequence of the data. We use the 8510, something like that. I cannot remember, but so using the same data, but B plus 3. Can you find any difference? This one and this one. This one. So we use the same data, 851731296, and got this. So first, leaf node has all the index key entry. 1, 3, 5, 6, 7, 8, 9, 12. Okay? And also, why don't you take a look at the node structure? Node structure, for example, the leaf node. Leaf node does not have children pointer, right? Because we don't need the children, we do not have, the leaf node does not have any children, so we don't need the children pointer. Okay? So there is no children pointer, instead it has one pointer at the end. That point what? Next leaf node, which is called sibling node. So sibling node pointer, which is not in the B3 index. We will see why and how we can be. Just I'd like to show the difference first. So it has the sibling node pointer. Another thing is, we do not have the children pointer in the leaf node. Then, can you see the difference between internal? These are the internal node, right? This is the leaf node. Can you find any difference?
Yeah.
Yes. What is different? No?
They don't have one.
Sibling. The internal node. This is called the internal, and and this is the leaf, or first level. So they do not have the sibling point. Okay, that's the first difference. Another one is
Do not define the data.
they have the internal node have the children pointer, right? Anyway, they need to point out the children, so they have the children pointer. And also, one last thing,
They don't have to define the data.
they do not have data pointer. No data pointer, no data pointer, no data pointer. However, if you see the leaf node, it has the data pointer, data pointer, data pointer, data pointer. Why? Because we assume to make the fully balanced. So when you access the data, 1, 1, 2, 3, 4. The 3, 1, 2, 3, 4. So all leaf node should have data pointer. Why? Internal node does not have the data pointer. So when you access the data 5, okay? How many IO do you need? Including data block. How many? How many? 4. 1, 2? No, there is no data pointer. Even though you find the 5 here, this 5 is not the index key value. This is just class 5. The equal or less than 5 goes to here. Bigger than 3 goes to here. So finally you can find index key value 5. So it has the data pointer, not this one. Data pointer, no, using this one, then you can find the 5 and lead and so on. So in this, the total 4. What about 8? How many?
4.
3.
Bigger than 5 goes to here, and 5, that's it? No, this 5 does not have data pointer. So bigger than 7 equal or less than 8 goes to here. Finally, you can find the data pointer 1, 2, 3, 4. What about 12? 1, 2, 3, 4. Always 4 iron. So using this index, Curie optimizer believe if I'm using this index, it will take the 4 iron. It's guaranteed. It's a fully balanced. So that is the reason it's called the B plus. It's the enhanced. It's a different version of the B3 index, B plus 3 index. At that time, this is called internal node. This is called the leaf node, first level node. Okay? If you already did by yourself for your phase 1 of the project B, you can understand right now why we need to keep the first level of the index. Okay? Because that determines the IO, that determines the speed. So that is B plus 3. Then problem is how can we build? Oh, one more thing. What about this theory? So let's say this table is the employee, where this is the ID. Index key value ID bigger than 5. How? So Curie optimizer decide to use this one. How can you search the data using this index? How many ID do you think to return this data using this index? It's very advanced level. How many IOs? Equal 5 is a 4, right? We already did. This is a 2. Okay, I think there's not too many. 2, 5 or 6. So let's start. So we decide to use this index for this query. So first, equal or the bigger than equal or less than 5 goes to here and goes to here. So how many IO? 1, 2, 3,
Four.
4. Okay? 4. Then, do I need to find the next from here?
No.
No. Because of the sibling pointer, we don't have to go up again. Just the next one. So, total 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is enough. What about the same query? Of this one. 5, 1. Okay? That's you need to next one. Access this one, then next this. You need to up and down, up and down. Okay? If you have the bigger the index structure, you need to access 100 times and up and down, it will be much more complicated. Okay, that's another benefit of using the B plus tree in case of inequality. Okay, that is the difference. Then let's see how we can build such an indexing B plus tree indexing structure. First, we need to determine node structure. So how many different nodes in B plus tree? 2 nodes. One is internal node. Does not need what? Data pointer, only children pointer. So in case of P is equal to 3, how many children? 3 children. Okay? So 3 children, how many index key entry? 2. Actually, it's not key. Okay, it's a separator. It's a classifier. So this is you don't have to actually I think that's it. This is an internal node. Then next one is leaf node. Leaf node, you should have the sibling pointer, not children pointer. Then how many index key entry? P minus 1, so 2. 1, 2. So we are going to use this one for the same data. So this is what first. Why don't we start from the beginning? So when 8 and 5 is inserted, we need the internal node or leaf node for 5 and 8. Leaf node always, because it's not actually grow up yet. So we need this sibling node pointer and 2 data is a leaf node. Then 5 and 8 are inserted. Then the next value is 1. What if 1 is inserted? It's a full. Okay, it's a full of data. So we have 1, 5, 8. We need to determine in case of full, always a split. So which one is the middle value? 5. Then we are not going to promote the value. Equal or less. This is the left hand side. And the others, right hand side. Okay, then it will be, we need to split into 2 sibling pointer. Okay? So equal or less, that's the difference from the B2 index. Because we need to keep all the index key value leaf node. So 1, 5, then 8. Then middle value, it's not called the promotion, but it's similar as the promotion. We can just create internal node. This is an internal node. Then 5 will be used for classifier. Okay. Then equal or less than 5 goes to left hand side. Bigger than 5 goes to the right hand side. Okay. That's it. Be careful. The middle value equal or less than middle value goes to left hand side. Others right hand side. That's it. There's one missing
The leaf point.
Sibling.
sibling node. But that's another thing. Then next, 7 is inserted. Always you need to find the leaf node. So bigger than 5. So we have space 7 and 8. The next one, 3. So 3 equal or less than 3 goes to here. So there's a full of leaf node. What happened? Split. 1, 3, 5. Which one is the middle value? 3. So each item index key entry goes to the left hand side. Which one? 1 and 3 goes to the left hand side, the other right hand side. Okay, so we can split into 2. So leaf node 1 and 3, and this is the 5. The middle value will be used for split. To split the data, classify 3 and 5. So it goes to here, and it goes to here, and this one goes to here. Don't forget the sibling pointer. This is a b plus 2. Next one, 12. 12 is bigger than 5. There is no space, so 7 and 8, 12. Okay? Then 8 should be here. Is there any space for 8? No. We can follow the same procedure as B3 index. So we have 3, 5, 8. Which one is the middle value? 5. So this is the, don't forget, be careful, these are the internal load. Okay? 3 goes to the left hand side, 8 goes to the right hand side, and 5 will be promoted like this. Internal load, when we split the internal load, we do not keep the middle value. But this one, keep it. Why? Because we want to keep all the index key entry in the leaf node. This 5 and this 5 are different. Okay? This 5 has the data pointer. This one just used for split into 2. So, finalize. Equal or less than 5 goes to here. Bigger than, equal or less than 3. Bigger than 3. Equal or less than 5 goes to here. This one. This one. Don't forget sibling pointer. Like this. Any questions so far? So, next one. 9. So 9, bigger than 5, bigger than 8, we have space. So 9 and 12. What about 6? Bigger than 5, less than 8. Even though we have space, we cannot use this one. Okay? So, final output, I think we have the final output. After we insert, even though we have the space, we cannot keep it. Why? Because the bigger than 5 goes to erase this one, so we need to split. So after we split, we can have this index structure, 6, 7, 8, then 7 is promoted, and so on. Okay, using this one. Any question first? What about the weird Oracle DBMS? B plus 3 in Oracle DBMS. Any difference? It's exactly the same algorithm. It's a very simple indexing structure. It doesn't take a long time, just 10 minutes. You guys can understand, right? So such a simple indexing structure has been used in most of the relational database model. So once you understand the algorithm, then you can implement it. Okay, that is another my favorite database project in this class. So sometimes I use the B plus tree or B tree index or something tree structure for the classroom project. But sometimes the query optimizer. Okay, so then what if 13 is inserted in this case? Why don't you draw the next change of the indexing structure? So what if the 13 is inserted after using this one. Bring your scratch paper, okay? Then put your name and ID and answer after 13 is inserted based on this one. Based on this is the last one. This is pop-up quiz.
Okay, next question.
Yes. Yes. You can start.
So,
What if 13 is inserted? It's not group. If you want, you guys can discuss, not loudly. Okay? Don't copy, but you can discuss with, you can ask to your friend. If you do not understand, you can ask to me, but do not copy.
so I have a question.
Yes.
So if one of the children of the state 4 is split within themselves, and then the left will go,
Including the middle value, and less than the middle value goes to the left hand side, the other right hand side. The middle value will be copied and promoted to the internal node. Then follow the same procedure and the
B tree.
yeah, B tree. Definitely this will be one of your final exam question. Okay. Because it's very easy to make the question. I can give the several numbers. The first thing is you need to decide the node structure and including node, leaf node, and the internal structure. They are different, okay, depending on the order P. Then next thing is, so whenever you have inserted data step by step, if you messed up the beginning or the other, cannot get ready. Okay, so you should be careful from the beginning, and also don't forget the details like the sibling pointer and data pointer not exist here, and data pointer and so on. Based on my experience, the half of the students never draw the indexing structure before final exam, really. Because it's easy to understand, so they believe they know how to construct. Yeah? But it's totally different. At least one time you need to try.
One last question. Small little question.
Yes.
So, in children, we insert your team. They say from left, so these two split.
Yeah, left hand side and this one right hand side.
But
The 12 will be promoted to year. Why? Because you need to split using that limit.
so the 9 and 12 will still be together.
Yes. This is the same as this one. Any volunteer? You want to solve the problem? Okay. Why is solving the problem? Why don't you grade by yourself? Okay? 0 to 10 scale. You still have a chance to revise while he solves the problem. Why don't you try to do this easier? Okay? extra credit.
Yeah.
Don't forget to let me know
Oh,
before semester end. Also, if you correct, you deserve the extra credit. If wrong,
No.
deduct a point.
That's not fair.
Okay? Is it correct?
Yeah, it's correct.
Yeah.
Okay, so as you can see, you can go back and let me know the before semester end. I will check the who got the extra point. Okay, so when 13 is inserted, okay, we do not have a space, so we need to split it into 2. So middle value is 12, so equal or less than 12 goes to left hand side like this, and right hand side the other. And then 12 it will be useful to separate. Unfortunately, there is no space for 12, so we can follow the same procedure as what you have done in the B tree. That's because this structure is the same as B tree. Okay? So 7, 8, and 12. So which one is the middle value? 8. Okay, so 8 will be promoted. Fortunately, there is a space. So 7 and 12. Somebody may be confusing because of 8 is not here because it's a B plus 3. No, this is here internally we will follow B3 index. This does not have any data pointer, so we don't have to hit. So just follow the B3 index structure. It's done. Okay, one more question. So we are going to insert the same value. That is 1, 3, 5, 6, 7, 8, 9, 12, and 13 for example here. So no matter what, am I correct or not? No matter what order of the sequence, as long as we insert this data, the output of index is the same. Am I correct or not?
Yes.
My question is, so sometimes I can insert 1, 3, 5, 6, and so on. Or sometimes I can insert the 8, 7, 12, the 5, 9, 3, 1. What about the output of B plus 3 index? Are they same
Yes.
or different?
It's same.
Same.
They're gonna be same.
Same. Only 3, 4, 5, 6, and different. Anyone who can justify why it's the same, why it's the different?
Because
Yes.
actually,
You are same or different?
Same.
Same. Okay.
We can either B plus 3
Mhm.
equal or less in the left and bigger than we're gonna point in the right. So it's always so it's, if it's equal, so it's always the left. It's unlike B tree. B tree is somewhat easier to change if you change the sequence of.
But
Mhm.
the only difference will be you will have more overflow if you have different sequence.
So you go for the
in the
difference?
in the process.
No,
No,
It's the same?
the same but like more overflow.
yeah, in the process,
Yes.
probably it's gonna be more steps.
Yeah,
It's a-
more splitting. More
But
splitting.
I'm asking the
It's
output.
output is same.
Yeah.
Same. Yes.
It's different.
It's a different?
Because it depends on the how we input. If we input like 1, 7, 3,
Uh-huh.
and next is the 7, and if the whole rate depends on how we split. If we split like up, then it will depends on the how splitting.
Different?
Yeah.
So do you have any additional opinion to that? Oh, yes?
I mean, if you insert it sorted, there's going to be there's going to be the first one will be filled in, but the second spot would be null or empty,
Mhm.
like the 3 up there. And if it's unsorted, sometimes there's chances that it'll be filled
Yeah.
in.
I think that in case of the order P is equal to 3, it's not easy to recognize. Answer is different. Okay? Why? Because if we have the more space, like the P order is 10 or 20, so Anyway, as long as the capacity reach the 50%, it will be split into two. The other 50% may not use the recently. So if we insert the data sequence worst case, always split half, split, then its capacity is 50%. Sometimes it can fill up all the data, right? So what? So for example, if we have the P is equal to 5, so we have the 1, 2, 3, 4, the leaf node data pointer.